a nail went straight through this battery. No fire, no explosion. Then it took 40 hours frozen and 8 hours of grinding just to open it. That's not a flex, that's a warning. Here's what you're actually signing up for if this pack ever needs repair. Before anyone could even open it, the second-generation Blade battery had already built a name for itself. And for once, the hype actually holds up under scrutiny. Instead of stacking individual cells into separate modules and then bolting those modules into a tray, BYD turned the cells themselves into load-bearing parts of the structure. There is no extra layer of casing sitting between the cell and the chassis. The cell is the chassis, at least in part. The numbers back up the ambition. The finished pack weighs roughly 572 kilograms and houses 170 long, narrow lithium iron phosphate cells wired in series. It can absorb charging power at the megawatt scale, which in plain terms means 1,000 kilowatts pouring into the pack at once. As of today, nothing else on the road charges faster, with Geely's newest LFP pack trailing in a close second. Safety is where the design separates itself from the pack. Engineers ground the casing down, hammered on it, and drove an 8mm nail straight through the cells. No fire, no smoke, no drama. For a chemistry that has, in past decades, occasionally turned violent under far gentler abuse, that result is not trivial. Lithium iron phosphate is already more thermally stable than the nickel-rich chemistries used elsewhere, but stability on a spec sheet and stability under a power drill are different things, and this pack passed both tests. Part of that resilience traces back to how the pack manages heat. Rather than circulating liquid coolant through channels, BYD relies on a refrigerant that changes state, evaporating to pull heat away from the cells far more efficiently than a simple fluid loop. It is cheaper to manufacture, lighter to install, and crucially, fast enough to keep up with that megawatt charging curve. Even so, surface temperatures during ultra-rapid charging climb to around 71 degrees Celsius, a number that would have been flagged as dangerous on older packs. On this one, the cell chemistry and the cooling system were built around each other from day one, so the heat is expected, managed, and survivable rather than catastrophic. The crew responsible for this disassembly were not amateurs. They had already pulled apart more than 20 battery packs from different manufacturers, and they broadcast this attempt live on Weibo, China's social media platform. From the opening minutes, it was obvious this one would be different. The first wall they hit was adhesive. Modern battery packs increasingly rely on structural glue to bond modules, bus bars, terminals, and even the wiring harness in place, the same basic philosophy Tesla uses in its 4,680 cell packs. BYD applied it generously, almost everywhere a seam could be found. That glue is precisely why the pack survives a crash test so well. Bonded structures distribute impact loads far better than bolted ones. But it also means the pack was never designed with disassembly in mind. Normally, technicians soften structural adhesive with heat guns or chemical solvents. Neither option is available here, because applying heat or aggressive chemicals near live lithium cells is asking for trouble. So the team chose the slow route, 40 hours in cold storage, hoping sub-zero temperatures would make the bonding agent brittle enough to crack apart. It helped, but only partially. Even after the freeze, 8 straight hours of mechanical force, grinding wheels, cutting tools, and sheer persistence were needed to actually expose the internals. What they found justified the effort. A ladder-shaped reinforcement frame splits the pack into distinct zones, with high-voltage compartments positioned at the front and rear, away from the passenger cabin. An integrated battery management system handles monitoring and balancing with fewer separate components than older architectures required, which trims weight and points of potential failure simultaneously. The energy density numbers told a slightly more nuanced story than the marketing materials. At the cell level, density measured around 180 watt-hours per kilogram, a touch below BYD's stated figure of roughly 192. At the full pack level, once you account for casing, cooling, and wiring, density settled near 132 watt-hours per kilogram. That gap between cell and pack numbers exists in every battery on the market. But here the integration efficiency, how much of the cell's raw potential survives the trip into a usable pack, came out at 73.6%. That figure is genuinely strong, and it explains why this architecture hits impressive range, despite using a chemistry that traditionally lags nickel-based cells in raw energy storage. Here is where the story stops being a celebration and starts becoming a warning. If it takes a trained team 40 hours of freezing plus 8 hours of destructive labor just to get inside this pack under controlled conditions, What happens at an ordinary repair shop after a collision? This is not a BYD-specific problem. It is the direction the entire EV industry is heading. Folding the battery into the floor of the car, making it part of the structural skeleton rather than a removable component bolted underneath, delivers real benefits. Lower center of gravity, better torsional rigidity, more usable cabin space, and meaningfully more range per kilogram. Every one of those advantages comes from the same decision that makes repair so difficult. Picture a moderate collision that cracks the housing or damages a corner module. An independent shop, without the specialized tooling or the patience for an 8-hour disassembly, would likely look at that job and decline it outright. Even a shop willing to try would face a structure that was glued, not bolted, meaning individual cell replacement is rarely realistic. In most real-world cases, the entire pack gets swapped rather than repaired at the component level. That trade-off has consequences well beyond the workshop. Insurance carriers already price in the cost of full pack replacement on heavily integrated EVs, part of why premiums on some models run noticeably higher than equivalent combustion cars. Collision repair bills climb for the same reason, and at end of life, packs bonded this thoroughly are harder to disassemble for recycling, meaning the process costs more, even though the materials inside remain technically recoverable. The Teardown team drew a parallel to Sandy Munro's well-documented disassembly of Tesla's 46 and 80 pack, where structural foam fills the gaps between cells and creates a near-identical headache for anyone servicing it later. Two competitors, on opposite sides of the world, arrived at the same engineering compromise independently. That is a sign the whole industry is converging on structural battery design because the performance upside is too large to ignore, repairability concerns notwithstanding. There is a genuine irony at the center of all this. The very qualities that make this pack safe and energy-dense, the dense bonding, the tightly integrated cell structure, the absence of loose modules that could shift in a crash, are the same qualities that make it brutal to repair. You cannot separate the engineering win from the serviceability cost. They are two sides of the same decision. The silver lining is the warranty math. Both BD and Tesla back these packs with roughly 8-year coverage in most major markets, meaning the manufacturer, not the owner, typically absorbs the cost if something fails inside that window. Predictably, the moment this teardown went public, brand loyalists pushed back, accusing the team of intentionally sabotaging the pack or rigging the temperature readings to make BYD look worse. The team's response was methodical. The cooling plate stayed fully intact throughout, and the only heat applied beforehand was a controlled discharge step, standard procedure used on every one of their previous 20-plus teardowns. Consistent methodology across more than 24 disassemblies is not exactly the profile of a hit piece. It is also worth noting the broader climate this story landed in. Just days earlier, a Chinese court ordered an unrelated automotive blogger to pay roughly $293,000 in compensation to BYD over claims the company successfully argued were unverified. Whatever the merits of that specific case, it illustrates how charged the environment around public EV criticism has become in China right now, and why a methodical, transparent teardown like this one carries extra weight. But none of that changes the underlying engineering reality. Pointing out a repairability trade-off is not an attack on the brand. It is simply naming a tension that exists across the entire industry, not just within one company's product line. Consumers keep asking for the same combination: longer range, faster charging, lower prices, strong safety. Manufacturers, BB included, keep finding ways to deliver exactly that. But every engineering decision carries a cost somewhere, and here the cost shows up years later, in collision repair bills, insurance pricing, and end-of-life recycling rather than at the moment of purchase. The good news is that the math is shifting in the right direction. Battery pack prices continue falling year over year, which means that even a worst-case full-pack replacement is far less punishing today than it would have been even 3 or 4 years ago, and that trend shows no sign of reversing. So no, this is not a reason to avoid BYD, Tesla, or any manufacturer building cars this way. It is the trade-off built into the most advanced EV architecture on the planet right now. Brilliant engineering rarely comes free. Sometimes the price tag just arrives later than expected.